Now I'm going to show you something that seems so fantastic, it seems too good to be true. But that's the power of mathematics and geometry, that if you put theorems and ideas and corollaries all together, we discover amazing things, not just about math, but about our everyday world. Look, check this out, because this is so awesome. All right, so to estimate the height of a statue, Holly steps away from the statue until her line of sight to the top of the statue and her line of sight to the bottom of the statue form a 90-degree angle. Her eyes are at 5 feet 6 inches above the ground, and she's standing 25 feet from the statue. The question is, how tall is the statue to the nearest foot? Now look, think about this for a second. Haven't you ever stood at some big statue or monument or some big building and looked up and said, wow, and it's really, really high. There's no way that you could actually take out a ruler, right, or measuring tape and measure it. How can you find the height of that? Well, the power of math and the power of geometry is that we can do that without having a really, really long measuring tape or scaling buildings in a sort of a dangerous, precarious way. In fact, we can use the power of the theorems that we've already developed. And this is really cool because you can do this. So here is this method that Holly has used, which is really quite clever. Now I drew it out here so we can look at this. So here's a little artist's rendition of what we have. I want you to understand a couple of things. This is just my version of it. This is not at all drawn to scale. And in fact, in most examples that we think of and look at and draw, we have to understand that things are not drawn to scale. If measurements are given, those measurements should go over and trump any particular visualization we may have. So understanding that, let's take a look. So what Holly did was she positioned herself so that her line of sight to the very top of the statue compared to the line of sight to the very bottom of the statue forms a perfect 90-degree angle. What we're trying to figure out is this length right here, the length of the height of the entire statue. So the height of that statue, that's what we want. We don't know that. In fact, we don't know this. In fact, we don't even know this. What do we know? Well, we know what her height is. So her height is 5 feet 6 inches. So actually, let me just draw in this extra little line showing her height across here. And of course, that's going to meet up at a right angle, which we like. We love right angles. Because notice what I actually did here was produce the altitude to this hypotenuse of this right triangle. Now we can actually apply that theorem that we've been talking about, how all three triangles, 1, 2, 3, are all similar. That's going to be the key to unlocking this mystery. Now we know this height because that's her height. So this height right here we know is what? Well, 5 feet 6 inches. Well, 6 inches is actually half a foot, so this is actually 5.5 feet. I'm not going to write feet, but we'll understand the units are feet at the end. All right, now, so that's easy to find because that's actually the height of where her eyeball is, and that's where she's looking. Great. Now, we also know, and this is easy to measure, how far she is from this line. You can sort of look, but then walk and measure this. That's easy to measure because it's on the ground, right? You can just use your feet to measure it, or a ruler. And you can see that, well, we're told that that's 25 feet. So that's 25 feet. Well, that's the same length as this. So this right here is 25 feet. And what I'd like to do is I'd like to find this entire length. I'm going to do that by first just finding this little length right here. If I could find that length right here, then all I have to do is add to it this known height of 5.5 feet. So if I could find this height, then the total height will be that height plus this. Well, now we can use similar triangles. Because what do I see here? I see a little triangle right here, right triangle, which is similar to this right triangle right here. And so what do I know? I know that big leg is to little leg as big leg is to little leg. And so I'm going to produce now a nice geometric mean here. If I call this height from here to here, let's say x, then I see that 25 is to 5.5, as x is to 25. Now where did that come from again? Where that's from? Well, remember, these two right triangles are similar by our theorem, and so what I see here is that big leg is to little leg of this triangle as big leg is to little leg of this triangle. So 25 is to 5.5 as x is to 25. Well, this is great. I use the cross product, and what do I see? I begin to see the geometric mean popping out because I see 5.5x equals 25 squared. And now I can actually solve this. And if I solve this for x, I see that x equals 25 squared divided by 5.5. And so if you approximate that, you would see 113.6, using a calculator, for example. So x equals 113.6. Great, that must be the height of the statue and we can have a big party. No, we have to think back and remember that's just this piece. I've got to now add on the base part here to get the entire height. So the total height is going to be 113.6 plus Holly's height to her eyeball, which is 5.5. And so when we add up these two numbers, I see 119.1. And if we round that to the nearest foot, then I see 119 feet. And that's the answer. That's the answer, but I must tell you, I think this is so cool. Because look, 119 feet, we could never climb up. I mean, we'd be climbing up and hanging onto the guy's nose and holding the thing there and trying to measure it and estimate it. We couldn't do it, and we could fall off into the guy's hand. We could hurt ourselves, but we don't have to. We can use the power of geometry and the theorems that we're looking at to do something very simple, to figure out the right distance to stand so that this measure right here is 90 degrees. Just measure that distance away and then use all the theorems we have. It's absolutely beautiful. That's the power of geometry. Congratulations, and I'll see you soon.